Welcome to Future Human Science, where we explore the cutting-edge technologies that are transforming our understanding of the world. Today, we're turning our gaze to the sky to explore how satellites are playing a crucial role in monitoring one of the most pressing issues of our time: climate change. Satellites are not only beaming down information from space, they are providing us with a detailed and continuous stream of data about the health of our planet. But how exactly do they do this? And what technologies make Earth observation possible? Let's break it all down. Our planet is a complex, interconnected system. To understand climate change, we need to measure a wide variety of factors: atmospheric conditions, land and ocean temperatures, ice sheet behavior, carbon dioxide levels, and the health of ecosystems across the globe. Ground-based monitoring systems, while important, can't provide the global picture we need. This is where satellites come in. Orbiting hundreds to thousands of kilometers above the Earth, these spacecraft give us a bird's-eye view of the planet, allowing scientists to track changes in real time and over decades. Satellites used for Earth observation can be categorized into two types: geostationary satellites and polar orbiting satellites. Geostationary satellites are positioned at an altitude of about 35,786 kilometers, where they remain fixed over a single point on Earth's surface. These satellites provide continuous monitoring of specific regions, making them ideal for tracking weather patterns and extreme events like hurricanes or wildfires. On the other hand, polar orbiting satellites circle the Earth from pole to pole at lower altitudes, around 700 to 800 kilometers. These satellites scan the entire globe as the Earth rotates beneath them, making them essential for long-term climate monitoring. But what makes these satellites so effective at tracking climate change? The answer lies in the sophisticated sensors they carry on board. These instruments can detect and measure a wide range of variables that are critical to understanding our climate. One of the most important tools is the radiometer, which measures electromagnetic radiation emitted by the Earth. Radiometers operate across various wavelengths, from visible light to infrared and microwave, allowing scientists to measure surface and atmospheric temperatures, as well as the concentration of greenhouse gases like carbon dioxide and methane. Another essential technology is radar altimetry, which measures the height of the Earth's surface with incredible precision. This technique is crucial for monitoring sea level rise, a key indicator of climate change. By sending radar pulses towards the Earth's surface and measuring the time it takes for the signals to bounce back, satellites can determine the height of oceans, ice sheets, and even land surfaces. This data helps scientists track changes in sea level, the melting of glaciers, and the thinning of polar ice caps over time. For example, the satellite missions known as Sentinel-6 and JASON-CS are specifically designed to monitor global sea levels and provide continuous data that helps us understand the rate and impact of sea level rise. Satellites also use a technique called gravitational sensing, employed by missions like NASA's GRACE, Gravity Recovery, and Climate Experiment. These satellites measure tiny variations in Earth's gravitational field, which can be caused by changes in the distribution of mass on the planet's surface. For instance, when glaciers and ice sheets melt, the redistribution of water affects the gravitational field, allowing scientists to track the loss of ice mass with stunning accuracy. These measurements have provided some of the clearest evidence of accelerated ice melt in Greenland and Antarctica. In addition to tracking sea levels and ice melt, satellites are essential for monitoring global temperatures, both on land and in the oceans. Using infrared sensors, satellites like NASA's MODIS, Moderate Resolution Imaging Spectroradiometer, and NOAA's AVHRR, Advanced Very High Resolution Radiometer, can measure the temperature of the Earth's surface and the atmosphere. These sensors detect heat radiation emitted by the planet, allowing scientists to track warming trends over time. This is particularly important in regions like the Arctic, where temperatures are rising faster than anywhere else on Earth, leading to rapid sea ice loss and permafrost thawing. Another critical tool for climate monitoring is the spectrometer. These instruments measure the composition of gases in the atmosphere by analyzing the light absorbed or emitted by molecules as sunlight passes through the atmosphere. This is how satellites monitor the concentration of greenhouse gases like carbon dioxide, methane, and ozone. For example, the OCO2 Orbiting Carbon Observatory 2 satellite provides detailed measurements of carbon dioxide levels in the atmosphere, giving scientists a clear picture of where emissions are coming from and how they are being absorbed by forests, oceans, and other carbon sinks. Meanwhile, satellites like TROPIME, Tropospheric Monitoring Instrument, help track air quality and monitor the emission of pollutants like nitrogen dioxide, providing essential data for understanding the links between climate change and human health. Satellites also play a pivotal role in monitoring the health of our ecosystems. Using multispectral and hyperspectral imaging, satellites can capture detailed images of the Earth's surface across a range of wavelengths. This allows scientists to monitor changes in vegetation, deforestation, and land use over time. For example, satellites like NASA's Landsat series and the European Space Agency's Sentinel-2 provide high-resolution images that allow researchers to track the deforestation of rainforests, the expansion of deserts, and the greening of previously barren regions. These observations are critical for understanding how ecosystems are responding to climate change and how changes in land use contribute to carbon emissions. Monitoring the oceans is another critical task for satellites. Instruments like microwave radiometers and radar scatterometers measure sea surface temperatures, ocean currents, and wave heights. For example, SMAP, Soil Moisture Active Passive, satellites can measure sea surface salinity, which is crucial for understanding the water cycle and ocean circulation patterns that influence global climate systems. Satellite data on ocean temperatures and salinity helps scientists predict changes in weather patterns, such as El Niño and La Niña events, which have significant impacts on global weather and climate. With this wealth of data, satellites are providing an unprecedented level of detail and precision in tracking the impacts of climate change. But the real power of this technology lies in the ability to observe long-term trends. Climate change is not something we can fully understand by looking at short-term fluctuations in temperature or sea level. It requires decades of continuous observation. Satellites provide this long-term view, allowing scientists to analyze patterns over time, detect anomalies, and improve climate models. These models are critical for predicting future climate scenarios and helping policymakers make informed decisions about how to mitigate and adapt to climate change. One of the most significant benefits of satellite technology is that it allows for global cooperation. Many Earth observation satellites are part of international programs that share data across borders, allowing scientists from different countries to collaborate on climate research. Organizations like the European Space Agency, NASA, and NOAA are working together to launch satellite missions and make the data freely available to researchers worldwide. This global approach is essential for tackling a problem as vast and complex as climate change. As we continue to face the challenges posed by a warming planet, the role of satellites in monitoring climate change will only grow more important. These technological marvels are providing us with the data we need to understand how our world is changing and what we can do to protect it. They represent the intersection of technology, science, and environmental stewardship, helping us make informed decisions about the future of our planet. Thank you for joining us on this exploration of satellite technology and climate change. If you found this video insightful, don't forget to like, subscribe, and hit the bell icon so you never miss an update from future human science. Together, let's stay informed and explore the innovations shaping the future of our planet. Until next time, stay curious,